Hello, everyone. This is Yonggan from Rice University. Today, I will present our work, Double-Win Quant, that is, aggressively winning robustness of quantized deep neural networks via random precision training and inference. Here's an overview of my presentation today. I will start from the background and the motivations of our work, and then briefly introduce the proposed Double-Win Quant framework and the evaluation results. We know that recent breakthroughs achieved by deep neural networks have fueled an explosive demand for DNN-powered intelligent IoT devices, which is still challenging due to the gap between the prohibitive cost of powerful DNNs and the limited on-device resources, as well as the vulnerability of DNNs against adversarial attacks. That is, an imperceptible perturbation in the input can mislead the prediction of DNNs. A natural solution is to combine existing defense methods with a most fine-grained compression technique like quantization. However, recent work shows that quantized DNNs are inferior in robustness due to the error amplification effect. So in this work, we ask a question that, can quantization be properly leveraged to boost robustness? To answer this question, we make the following contributions. First, we propose a new perspective about the role of quantization in DNN robustness. We find that if properly exploited, quantization can enhance DNN's robustness by a notable margin. And we discover the poor adversarial transferability between different positions of adversarially trained models. And based on that, we propose the Double-Win Quant framework to aggressively boost quantized DNN robustness. We validate DWQ's effectiveness across 4 adversarial training methods, 4 models, 3 datasets on the various attacks. Here are the motivating observations for our Double-Win Quant framework. Here, for an adversarial training model, we directly quantize it to an attack position to generate the adversarial attacks, which are used to attack another inference position, and we visualize the robust accuracy here. From the comparisons between the diagonal and non-diagonal elements here, we can identify the poor adversarial transferability between different positions, which is consistent across different adversarial training methods and training positions. We analyze the reason behind the poor adversarial transferability is because adversarial perturbations are shielded by the quantization noises between 2 positions, and such noise cannot be effectively learned by gradient-based attacks. Based on that, we propose the Double-Win Quant framework with randomly precision inference. So we randomly select one position during inference, and the motivation for this simple but effective technique is that recent works find that if we directly quantize a DNN to different positions, it can have relatively stable natural accuracy on clean images. While this will notably degrade the attack effectiveness due to the mentioned poor adversarial transferabilities between different positions. To further enhance DWQ's effectiveness, we propose the random position training to equip the models with switchable batch normalization layers and randomly select one position during training. The motivation is that applying independent batch normalizations to record the statistics of different positions can further increase the difficulty of transferring adversarial attacks between different positions. We next evaluate Double-Win Quant on top of 4 networks, 3 datasets, 4 adversarial training methods under different adversarial attacks. Here, we evaluate Double-Win Quant on CIFAR10 datasets. We are applying DWQ on top of 3 adversarial training methods and 2 networks, and we find that DWQ consistently outperforms the total adversarial training methods, and the enhanced DWQ achieves the best robustness with up to 14% higher robust accuracy over the full position models. And we find that DWQ shows good scalability to large-scale datasets like ImageNet, with both better natural accuracy and robust accuracy. We also evaluate DWQ against more attacks like auto attack and CWIN's attack, and we can observe a consistent improvement in robustness here. So that's all for the presentation today, and for more detail, please refer to our paper.